we've introduced propositional logic. So in this section we look at some applications. Alright, this first part, translating English sentences. Yeah, we can make sentences sort of logically precise by writing them in terms of propositional logic. Here's an example. Translate this into a logical expression. This sentence: you can board the plane if you have a ticket and a valid passport. So how can we turn this into a logical expression? Well, we're looking for these words: and, or, not, and if. So those are our logical operations. Yeah, there might be other words that have the same meaning. And we also need propositions, so we can use these propositions. So P says you can board the plane. Q says you have a ticket. And R says you have a valid passport. Okay, so we're using these three propositions. And yeah, here we see an if. Okay, so there's an implication here. So if you have a ticket and valid passport, then you can board the plane. So that's the implication. And there's also an and here. Okay, so I hope you see. Yeah, so you have a ticket and your passport is valid. That implies you can board the plane. Alright, so this is the translation. Okay, in the book. This example, you can access the internet from campus only if you are a computer science major or you are not a freshman. Right, so we see the operations, yeah, only if. So that's an implication, and the operation or here. And breaking up, so the propositions, so A is the proposition: you can access the internet from campus. Yes, remember, only if, that just means an implication. So A implies this stuff. So yeah, C is the proposition: you're a computer science major. And here F is the proposition: you're a freshman. So we want the negation of that. And the operations or. So we end up with this. Yeah, so you can access the internet from campus implies you're a computer science major or you're not a freshman. Alright, so that's not too bad. One more. You cannot ride the roller coaster if you are under 4 feet tall, unless you are older than 16 years old. Yeah, these are definitely confusing. Yeah, I find them confusing. Can we see the operations here? Yeah, we have an if. And what's this? An unless. Yeah, so different ways to think about this. So that we have an if here. So if you are under 4 feet tall, okay, then you can't ride the roller coaster unless you're older than 16. So if you're older than 16, then you can ride the roller coaster. So the problem is, yeah, if you're under 4 feet tall and you're younger than 16, then you can't ride the roller coaster. Yeah, so this unless means really and not. Okay, so and you're not older than 16, that's the problem. Okay, so R is the proposition you're under 4 feet tall. S is the proposition you're older than 16. So if you're under 4 feet tall and you're not older than 16, that implies you cannot ride the roller coaster. Q is riding the roller coaster. Yeah. So so that gets the meaning of the sentence. Basically, anybody can ride the roller coaster except the people that are under 4 feet tall and younger than 16. And so that's what this is saying. Yeah, tricky and confusing. Propositional logic can be used to check if a set of conditions is consistent. This means it's possible to satisfy all the conditions. Conditions would be inconsistent if it's impossible to satisfy them all. Alright, so here's an example. Suppose a celebrity is hiring a personal assistant. Well, they have these conditions. You must speak 3 languages or be 30 years old or younger. Alright, so either you speak 3 languages or you're younger than 30. You must not use Twitter, or you could be over 30. Third condition, if you use Twitter, you must not speak 3 languages. Alright. So are these conditions consistent? So do any possible applicants exist that satisfy all 3? Okay, let's first convert these conditions into propositional logic. So there's really just 3 conditions here, combinations. Let P be the proposition that the applicant has age less than or equal to 30. Q says they speak 3 languages or more, and T says they use Twitter. So the first condition is P or Q. Okay, so their age is less than or equal to 30, or they speak 3 languages. That's the first one. The second condition, the negation of T, so they do not use Twitter, or they're not younger than 30. Okay, so that's the second condition. All right, and the third condition, if they use Twitter, if T is true, then they must not speak 3 languages, then not Q. So this shows us exactly what the conditions are. So can all 3 of these be true? Well, let's take that's one way to kind of analyze this situation, just to look at different cases. Let's look at using Twitter. Okay, so two of the conditions involve Twitter. Okay, so if T is true, okay, so then using this condition, okay, so if T is true, then the only way this implication can be true is if not Q is true. Alright, so remember, an implication is false if you have a true implying a false. So this not Q must be true. Well, that tells you that Q is false. Now if Q is false, then looking at this condition, so if Q is false, so we have P or Q, well, the only way this condition can be true is if P is true. So false or false is false, but true or false is true. Okay, so P must be true. But then we get a problem with the third condition. So if P is true, then this is false. Not T is also false. So then this condition is false. All right. So if the applicant uses Twitter, then we can make these 2 conditions true, but the middle one is false. All right, so that's telling us that combining these 3 conditions, the applicant cannot use Twitter and satisfy all 3. So if they don't use Twitter, okay, so if T is false, little t, then this the implication is automatically true. If T is false, then not T is true, and then this or is true. So then we just need either P or Q to be true. So if the applicant doesn't use Twitter, then if they're either age under 30 or speak 3 languages, then they satisfy all 3 conditions. All right, so these conditions are consistent. It is possible to make them all true. For example, an assistant that is under 30 and doesn't use Twitter satisfies all 3. All right, so I hope that made sense. So yeah, again, we're looking at these propositions. They're either true or false. So only finitely many cases. Yeah, just 8 possible cases for 3 propositions. Yeah, we could have made a truth table here. Look at all the options, the 8 cases. Okay, next, Boolean searches, another application of a logic. So, right, if you're using a search engine like Google, and you type in some words to search for, then it automatically assumes you're looking for pages that contain all the words. So it assumes that you're using and. So if you search for George Boole, that's the same as you're looking for George and Boole together. You're looking for pages that contain both words. Yeah, so if you look on the Google search help page, it says, yeah, you can use or between words to combine 2 searches, so looking for one word or the other. But yeah, I tried it and it just seems to use and, so if you do 2 words with an or, it seems to look for both words together. So I'm not sure how the or part works. But yeah, more useful thing when you're searching is the not operator. So if you're looking for one word and not another word, on Google you can write not with a minus sign. So for example here, yeah, if you search for logic on Google, you come back with an Apple product and a wrapper. So to get rid of those things you don't want, yeah, you can search for logic minus Apple and minus wrapper. Okay, so that means you're looking for logic, the word logic, and not the word Apple, and not the word wrapper. And then that search returns logic in computer science, for example, Boolean logic. Alright, so so certainly the not operation is useful when you're searching. And the last application we'll look at are logic puzzles. Yeah, I enjoy puzzles myself, but yeah, if you enjoy puzzles, these logic puzzles can be challenging, hopefully also fun. Famous examples of logic puzzles are set on an island where people there are 2 types of people. The first type always tells the truth. Call those knights. The other type always lie. So those are knaves. So if you meet someone on this island, you don't know if they're a knight or a knave, but just by looking at what they say, you could try to work out which is which. Alright, so in this example, you meet 2 people called A and B on this island. A says, we're both knights. B says, A is a knave. So can we work out, are they knights or knaves? A and B. Okay, yeah, so there's only 4 possibilities. They're either both knights, both knaves, or a knight and a knave, or a knave and a knight. So which is it? Well, suppose A is a knight. Okay, then he's always telling the truth. So then A and B must both be knights. But if B is a knight, then what he says has to be true, so he's saying A is a knave, but that contradicts our assumption that A is a knight. Alright, so that doesn't work, so that tells us that if you assume that A is a knight, then you get a contradiction, so that cannot be true. So A must be a knave. Okay, so if A is a knave, then everything he says is false. Okay, so they're not both knights. Right, and yeah, so A is a knave, so, but that doesn't tell us about B yet. So B could be a knave or a knight. But B says A is a knave. Okay, and that's true. So B told the truth here, so B is a knight. Alright, so the only way the only possibility for these 2 statements are that A is a knave and B is a knight. Alright, so you see how this works? Yes, you're just looking at the different possible cases. And just remember, your knights, everything they say is true, and knaves, everything they say has to be false. Example 4. Is it possible for someone on the island to say, I am a knave? A solution, it's not possible. So can you see why? Alright, so yeah, if you just have to look at the 2 cases. So suppose the person is a knight. Well, that doesn't work. If they're a knight, everything they say has to be true, so they can't say they're a knave. And if they're a knave, everything they say has to be false, so they can't say they're a knave. Alright, so nobody on the island can say this statement. Alright, so yeah, another example of consistency checking here. Boolean searches. Logic puzzle, another one. Okay, so in this example, yeah, you meet a different A and B. A says B is a knight, and B says the 2 of us are opposite types. Okay, so can you work out who is a knight and who is a knave? Okay, yeah, so we can try the same strategy. So first, assume that A is a knight. Okay, so if A is a knight, then what he says is true, so then B is a knight. But then that doesn't work because B is a knight, what he says is true, but what he's saying here is not going to be true in this case if they're both knights. So again, yeah, this is similar, so that tells us that A has to be a knave. Alright, so if A is a knave, everything he says is false, so that means that B being a knight is false, so B has to be a knave. Okay, and does that work with what B says? Yeah, so A and B are both knaves, and so everything that B says has to be false. And yeah, so the two of us are of opposite types. Yeah, that's false. They're both the same type, both knaves. All right. Okay, well, last one. Yeah, this muddy children puzzle. In the case of two children, yeah, you could have any number of children, but yeah, let's just do it for two. Okay, so two children playing in the backyard. They both get mud on their foreheads. The father says, at least one of you has a muddy forehead. And he asks the children to answer yes or no to the question, do you know whether you have a muddy forehead? Okay, so what happens is that the father asks the question twice. What will the children answer each time this question is asked, assuming that a child can see whether the other one has a muddy forehead, but can't see their own forehead. And yeah, we're assuming both children are honest and that they answer each question at the same time. We're also assuming that they're logicians. Alright, so the first time the father asks, do you know if you have a muddy forehead? Well, each child can see that the other child does. They don't know about their own forehead, so they both answer no to that question. Alright, now the father asks again. And now the children can use the fact that that the first answer was no. So why is that? So yeah, so now that the children are thinking, oh yeah, so So yeah, the father also said, at least one of you has a muddy forehead. So that means, yeah, for the first question, yeah, if one child had seen that the other did not have a muddy forehead, then they would have been able to work out that their own forehead was muddy. So then both answering no for the first question means that they can both answer yes. For the second question, yeah, they can work out that they must have a muddy forehead themselves. All right. Yeah, definitely confusing. All right, so that's some logic puzzles.